I'd like to introduce our last speaker of the day, Tiago Fonseca, who'll be talking to us about single-valued integrals and modular forms.
Thank you. Thank you, Bryce, for the introduction. Let me thank the organizers for the invitation. In fact, it's not the first time I speak here at NIMPA, but it's the first time I speak in a number theory workshop, so I'm really happy, and I really thank the organizers for the initiative to organize this conference. Okay, so this is the title of my talk. I'll talk about single-valued integrals and modular forms. And that's more or less how the talk will be distributed. I will start by discussing this concept of single-valued integrals. Now, this is a relatively recent concept that was developed by Francis Brown and later by Francis Brown and Clément Dupont. And it comes from considerations in certain parts of arithmetic geometry, and it has applications in physics as well. But I think this concept should be better studied in number theory. And so my intention here is to explain a little bit what this is and to show how this is related to some particular number theory problems connected to modular forms. Okay, so I'll start by trying to motivate this concept of single-valued integrals just with an example, very simple example. So everyone is familiar with the complex logarithm. Okay, so we all know that if you want to compute the logarithm of a non-zero complex number. So this is not well defined, right, for an arbitrary non-zero complex number. So we all learn in our first complex analysis course that you have to choose a branch of the logarithm, and then you can really attribute a value to that. So the explanation for that, one way to understand this. This phenomenon is the explanation for that is topological, right? So you can define the logarithm as an integral of this differential form on the complex plane minus the origin. So it's an integral from 1 to this complex number a. Okay, but you can take such an integral in many different ways, right? So here's 0, here's 1, and here's a, some complex number. You can choose a path like this. But you could also, I don't know, like turn around the origin here, choose another path like this. Right? And then the values of this integral along these different paths will be different. And that's why this function here is what people in the old days would say it's a multivalued. It's not really a function, it's a multivalued function. Right? And it depends on the path of integration. Okay? So another way to phrase this is in terms of a certain action of the fundamental group of the complex plane. So this is the complex plane minus the origin, which I denote C star. And we call this action monodromy, right? So it's the, in this case, it's the effect on this function when you turn around the origin, okay? And again, we all know this. Whenever you turn around the origin, this function gets transformed by, you get some 2 pi I here. which, of course, it really corresponds to the fact that if you integrate dz over z over a positively oriented simple path here around 0, you get to pi I. Okay? And so that's the action of monodromy in this case. Okay, but so if you want now to get a single valued function, okay, so in this case, what you can do is very simple. You want to, in some sense, you want to kill this monodromy action, or which amounts to choosing a path of integration. And in this case, what you can do is simply you can consider log A plus log A bar, right? And this function is just this function, log absolute value of A squared, okay? And then you can see here, and also from the explicit formula, now you have a single valued function, okay? So this function is single valued. We can also express it in terms of an integral also equal to like a single integral. So here you would have like some combination of integrals because this is an integral and this is an integral. One way you could write this as some kind of integral involving dz and dz bar would be something like that. So integral on P1 g log z minus a, z minus 1, wedge dz bar over z bar. You have to be a little bit careful with this because these functions have singularities and you have to deal with that. But you also have formulas like this, okay? All right. So you'll see where the number theory will come in a minute. But before that, there's another way of understanding this, this process of starting from a multi-valued function and getting a single-valued function, which has to do with cohomology. So I'll just do this very simple case here. So there's a cohomological interpretation. Which is the following. So you can consider in a more structured form, this integration is happening when you consider the cohomology. So the RAM cohomology has to do with differential forms of C star relative to this boundary here of integration. So this relative cohomology will have a basis given by the following differential forms. And what people in arithmetic geometry call Betti cohomology, but it's just singular cohomology. So this is just the dual of the singular homology. And it has basis, right? I'm going to call that delta dual and gamma dual, where delta is this path, so some path from 1 to A, and gamma is this circle that turns around the origin in the positive direction. Okay? So whenever I have this situation where I'm computing two different kinds of cohomology of something, I can try to compare these two cohomologies. And this is classically given by de Rham's theorem that says that to compare both cohomologies, to go from one to the other, we just integrate the differential forms. Okay? And what you get is something that we call a period matrix. Okay? So period So it's giving the comparison, de Rham versus Betti. Okay, and this comparison is given by integration explicitly. Integration. Okay. So in this case, the period matrix is a 2-by-2 matrix. So here I put the de Rham basis. And the matrix is given by integration. So I integrate this form against this path. I get 1. Here I get the logarithm. Here I get 0. And here I get 2 pi. OK? So when you formulate things like this, the action of monodromy, so this action of the fundamental group, so what's happening after you turn around the origin, becomes a matrix multiplication, monodromy. So P, the matrix P, gets transformed by something like this in this case. So multiply by this matrix here, which has coefficients, well, in Z or in Q or in R, in this case. So with this gadget here, you can now build a new matrix, which in the theory of Brown and Dupont, they call the single-valued period matrix. Okay, so it's a very simple formula. So the single-valued period matrix. So here's this word single-valued. And the formula is as follows. It's the new matrix S, which is P bar minus 1 times P. Okay? So in this case, if you do this computation, you're going to get 1 log absolute value of A squared, 0, and minus 1. Okay? And this new matrix has no monodromy, of course, because these functions are single-valued. But you can also see from this formula that you're killing, when you do this operation here, you're killing the action of the monodromy operator. Okay? So no monodromy. Okay, so now the main point is that this example I just explained, this formula here is quite general and works in very general situations. Okay? So they build up a theory around this where, so the original motivations come from understanding this process of passing from a multi-valued function to a single-valued function, which appears in many problems related to special values of L functions where you have, for instance, polylogarithms. But really what appears in the formulas are not the polylogarithms themselves, but what people call the single-valued cousins of these polylogarithms that people sort of came up in ad hoc ways. And there's a theory that explains, in general, how you can get these functions in a very uniform manner. Okay? So that's one of the original motivations of the theory. So let me just say very vaguely, so that there's a general, and here I'm gonna say, put a word arithmetic theory. Developed by Francis Brown and Clément Dupont. There's a very nice paper, 21, on this. Because, why do I say arithmetic? Because now, of course, I motivated this and the terminology in terms of functions, but you can apply this formalism to get numbers which they call single-valued periods. So here you have functions because you're sort of varying this A here. But you could fix A. And so this is saying that, for instance, if A is an algebraic number, log of absolute value of A squared is a single-valued period. Okay? And so there's this arithmetic notion of what single-valued periods are, and they're given by something like this. So again, I'm going to be very vague because this is not very important. I'm going to give an explicit example in the second part of the talk. So given H de Rham and H Betti, so some cohomology. So these are going to be Q vector spaces, which you should think as cohomology given by cohomology of algebraic varieties defined over Q or over Q bar, over the algebraic numbers, okay? So there's an algebraic de Rham cohomology where you only deal with differential forms over the rational numbers. And this is the usual singular cohomology. So you get two different vector spaces, Q vector spaces. And again, you can compare them via integration. You get a period matrix. So you can compare them. So there's an isomorphism like this when you base change to C. Which is the comparison isomorphism. And you get some period matrix, which is this matrix. It's going to be a square matrix which represents this isomorphism here. And the entries are going to be transcendental numbers, which we call periods, which are roughly given by integrals of differential forms with rational coefficients over some topological cycles. And these we call periods. So they are usually transcendental numbers of arithmetic interest. So you get and this we call the period matrix. Period matrix. But you can also, in the theory, consider this other matrix from which you can build up from the period matrix. So this matrix is invertible, and then you can consider this. And here, the thing is, you get some matrix with coefficients in R. Okay, so the single-valued period matrix will give you a matrix with coefficients in the real numbers. And so the idea is that we've seen many examples of this in this conference. When you have, for instance, special values of your functions, you see often the special value is a real number. It's not a complex number, right? And this real number will involve some rational numbers related to the arithmetic invariance of your situation, and then some transcendental number, which is usually given by a regulator, and then there's a period. But these things often are not just periods. They are single-valued periods, which is a more precise way of describing these numbers. Okay? So this, in general, these single-valued periods will be real numbers of arithmetic interest. Okay? And the emphasis here is on real. And here I'm doing over the rational numbers just to simplify. But let me just put this phrase, also a version over number fields, but then you have to consider all the different embeddings, and I don't want to also a version over number fields. Okay? So here's a very simple example. This was mentioned in Janine's talk. So we have the classical analytic class number formula, right? Which gives you the residue of a Dedekind zeta function. Oops. At 1. So this is Dedekind zeta function. And so there's a very precise formula for that. I'm going to ignore the rational numbers that appear. And then there appear some transcendental numbers like a power of pi. Square root of the discriminant. And then this determinant of logarithm of all the embeddings of the number field computed at some certain units. And this is what we call the this is the most classical regulator, right? Is the co-volume of the lattice given by the units of the number field by this log embedding. And it appears as a special value of some kind of zeta function. And you see in this formula, what appears here is log of absolute value of something. And so these guys are not just periods, they are single-valued periods. So this is one of the first instances where you can see this, phenomenon where what often appears in this theory of special values is not really just periods, but single-valued periods. Okay? So I could give many other examples. So you can phrase Archimedean heights in terms of single-valued periods. Other special values of L functions. So the integral that appeared in Janine's talk as well, like something like that, integral of omega bar is a single-valued period, and so on. Okay. But now I want to restrict to, so that's my brief introduction to single-valued periods. Now I want to show this in action in an example that comes from number theory, how this philosophy can be used to shed some new light on very classical objects, which has to do with Poincare series. Okay, well, that's where the modular forms will come in. So Poincare series. Okay, so this is very, very concrete. Okay, so this Poincare series are a very explicit way of constructing modular forms. Okay, so in this case, for this talk, I'm going to consider. So they will depend on certain parameters, the weight, and the weight will always be even for me. Okay, the level of the modular form is the same level that appears in Janine's talk, is gamma naught of n. So this is the group, the Hecker's congruent subgroup, right? A, B, C, D, SL2 of Z, such that, let's write like this, n divides C. So this is a subgroup of SL2 of Z. And the Poincare series, so I should put here more decorations, so I should put a K and an N, but I'll just write like this for simplicity. So this will be some explicit function given by a series, okay? So this particular formula here only converges absolutely for K at least 4. If K is 2, you have to do something slightly different. And that's the expression for the Poincare series. So it's sort of going to average over these exponentials like this. Weight k. And you're going to sum over all the elements in the group modulo the stabilizer of the cusp at infinity, which is just given by the condition C equals to 0. Okay? So this gives a subgroup of this group here. And this subgroup, you can see it acts trivially here because I have the exponential of 2 pi I times an integer. And so this is well defined. And you can consider this infinite sum here. And this gives what we call a Poincare series. So Z lives in the upper half plane. Okay, so that's the upper half plane. So this is an example of a modular form, right? It's some function that transforms like this under the action of the a certain subgroup of SL2 of Z. And M here for me, so you see it depends on this extra parameter here, M. And M for me is any integer, okay? And this integer, so M, I call the index. Okay? So for any, so if I fix the weight and the level, I have an infinite number of Poincare series parameterized by the integers. Okay? So these are indeed very classical modular forms. They go back to Poincare himself. They play an important role in the theory because if you consider positive index, so m greater than 0, these guys are going to give cusp forms. And in fact, they're going to generate the space of cusp forms. If you consider, so they're kernel functions for the Fourier coefficients. And if you consider m negative, they're going to have, they're not holomorphic modular forms. They're what we call weakly holomorphic modular forms. They have a pole at infinity. And they also appear in many classical works in number theory. And the way they appear is related to their Fourier coefficients, which you can compute very explicitly. So here's the formula. So Fourier series of the Poincare series. So you can write your Poincare series as any modular form. You can write, you have some Fourier expansion. Okay? So I'm going to call this Fourier coefficients AN, where Q is e to the 2. So this is an analytic number theory conference, so it's EZ. Okay? So that's the Fourier expansion. You can prove it's of this form always. So it's Q to the M plus, I'm going to sum just for n greater than 1, and some coefficients here. So you can see from this formula already that if m is positive, this is going to be a cusp form. And if m is 0, this is going to be an Eisenstein series. And if m is negative, this is going to have a pole at infinity, right? If m is negative. So, and then these coefficients are very explicit. So you can compute them. You just compute the Fourier transform. And this is done in Poincare's paper. So here's the explicit expression. So lambda mn. So 2 pi minus 1 to the k over 2. Then an infinite sum here over multiples of n. And here you have a Klosterman sum that appeared in Bryce's talk. And then you have some values of certain functions called Bessel functions. So this is the formula if m is positive. If m is 0, I don't really care too much in this talk because it's an Eisenstein series. And if m is negative, you have a very similar formula. Oh, I forgot one term here. So there's the term n over m, k minus 1 over 2. N over absolute value of m, k minus 1 over 2. And then some very similar formula, Klosterman sum, c, I. So now you have an I Bessel function, which is some variation of absolute value of n of the J Bessel function. So let me write here. So K stands for Klosterman sum. Okay, refer to Bryce's talk. And I and J are Bessel functions. It's not very important. Actually, a curiosity. This was done before Klosterman, right? So Klosterman sums appeared in Poincaré's work before they were called Klosterman sums. And they appear in this formula for the Fourier coefficient of the Poincaré series. And so this formula has, this kind of formula has been applied in a number of problems which relate to computing growth of Fourier coefficients of modular forms, right? Because you can express them in terms of Poincaré series. And then for Poincaré series, you have this very explicit expression for their Fourier coefficients. And then you know how to estimate Klosterman sums. You know how to estimate these functions here. And then you get estimates for growth of modular forms, both in the case of cusp forms and in the case of weakly holomorphic modular forms. Right? There's classical work of Hademahe on partition function that uses estimates of these kinds of stuff here. But you can see this is very, so you're going to have some real numbers that are given by this crazy formula. And it's very hard to understand the arithmetic nature of these numbers, for instance, when they vanish, when they're irrational, things like that. So you have, this formula is very useful for certain analytic considerations, but they're very hard to understand from an algebraic point of view. So just to give a very explicit example, so let's take weight 12 and level 1. So we know cusp forms is generated by this Ramanujan's delta function. So the first Poincaré series is going to be some multiple of delta. And this multiple is just going to be the first Fourier coefficient of the Poincaré series. I need some number. Like I'm going to give here first digits, some real number. Looks very transcendental. And in principle, you have an explicit formula for all the Fourier coefficients of delta using this. Okay? But this formula doesn't help you. So there's another conjecture of Lemmer. I think it's still a conjecture. Someone correct me if I'm wrong. Which relates to understanding when the Fourier coefficients of the Ramanujan's delta, which are integers, when they vanish. So the conjecture is that they never vanish. And you could say, well, I could try to apply this and understand this conjecture through this point of view, but it's completely unhelpful, right? In fact, Lemmer's conjecture is equivalent to proving that this Poincaré series doesn't vanish identically for every m in this level and weight. So and we don't know how to prove even that. Like so this formula is very useful for estimates, but it's not clear at all what's happening in terms of the arithmetic nature of these coefficients. Okay, and some very strange things. So it looks very transcendental, right? I mean, you have these strange formulas, but some weird phenomenon can happen. So, for instance, here, this example was dealt with by Brinier, Ono, and Rhodes. Okay, so you start computing with this. So you take weight 4 and level 9. Consider p minus 1. Okay, it's a weakly holomorphic modular form. So it has a pole here of order 1. And then you start computing the Fourier coefficients, and they look to be integers. Again, they're given by the same crazy formula, but now they're all integers. Right? And in fact, they prove this using harmonic mass forms. And then later there's a geometric interpretation by Candelari, which is more or less in the sense of what I'm going to say here. Okay, CF Candelari. So you have all this weird phenomena where this Poincare series, which in principle the Fourier coefficients are very transcendental numbers, but they become sometimes they're rational, sometimes they're not. Most of the times they're not. Sometimes they vanish, sometimes they don't. And you would like some way of understanding this. So here comes a theorem, again, in a very vague form, because I don't have time to explain precisely all the objects. So you see these Fourier coefficients are some real numbers that are most often than not transcendental. And what we can prove is that actually they are single-valued periods in this sense I explained to you. So are single-valued periods. Now, this statement can be made much more precise. I'm going to make it slightly more precise. So what happens is that you have some matrix S of single-valued periods, single-valued period matrix of, and then it's associated to the cohomology of some very precise age of some very precise algebraic variety. So this is called a Kuga-Sato variety in arithmetic geometry, which will depend on k and n, on the weight and the level. And this theorem says that actually, if you take the field over rational numbers generated by all the Fourier coefficients of all the possible Poincare series in this weight and level, so it's some transcendental extension in general. But this field is the same field generated by the coefficients of this matrix here. So there's an R here, which is the rank of this matrix, the size of the matrix, and also depends on this K and N. Okay? So this theorem in vague form is saying that you have formulas relating the Fourier coefficients of Poincare series to certain integrals that you compute on some algebraic varieties related to your modular forms of given weight and level. Okay, and so these numbers here they include things that appeared in previous talks, like so includes Peterson norms, for instance, or Peterson inner product. But also some non-standard constants that, as far as I know, they don't appear before. So let me just give a very explicit example. So that's the statement in the general form. So let me give you explicit example so you can see this. So in practice, we can actually compute this. So in this case, for weight 2 and level 11, this Kuga-Sato variety will just be some modular curve. And this modular curve in this case is an elliptic curve, which you can give a very explicit equation. And then you get, for instance, the formula just to give you an explicit formula. Minus 1, where this omega 1, eta 2, etc., they are just integrals over this elliptic curve. So I'm just going to write one of them. Okay. So these formulas in the theorem, so the theorem is saying that there are some formulas, some rational formulas relating both quantities. You can make them very explicit depending on the case. Okay. And so what this does for you, not going to write here like a list of corollaries. Let me just explain very vaguely. Is that actually this this formulation of these Fourier coefficients in terms of single-valued periods, it sort of explains all the rationality phenomenon that I know on these Fourier coefficients. So whenever they're rational, the explanation is really cohomological in some sense. It's related to this formula. For instance, if this is a bit silly, but if this rank is 0, which happens sometimes, then there is no single-valued period matrix, and this formula is implying that all these Fourier coefficients are rational, for instance. And you have more explicit formulas that also explain other. So this, again, this is related to CM modular forms, which is related to the fact that this cohomology here that appears has endomorphisms, and this immediately implies that this, when you have those formulas, that these Fourier coefficients are going to be rational, and so on. There are all the cases I know where you have this strange phenomenon where you're getting rational Fourier coefficients, you can explain very easily through this point of view. Okay, so let me just put this as a remark. So, so theorem explains, let's say, rationality phenomena of AN of the Fourier coefficients. It also allows you to translate questions about the arithmetic nature of these Fourier coefficients to, in terms of something known as the period conjecture. So we understand conjecturally very well the algebraic relations the periods should satisfy. And once you have an interpretation of numbers in terms of periods, you at least know what you should expect in terms of their transcendence and their algebraicity. And so this connection allows you at least to make predictions of when these things should be transcendental or algebraic or rational. So the period conjecture informs you on the arithmetic nature of these numbers. And I don't have time to discuss the proof, but let me just say that the proof of the theorem. So the proof relies on, proof relies on stuff that I didn't tell you on this formalism of the single valid periods, plus the theory of harmonic mass forms. So there's a very analytic part which sort of where you can use this theorem of Brinkmann and Ono on mass Poincare series. And then you combine this with some algebraic arguments to get. So you have to relate this theory of harmonic mass forms to this theory of single valid periods, in this case of modular forms. And once you do that, you can sort of translate what people do in this theory of mass forms into this theory of periods, and then you can get results like this. Do I have more time, or yeah? So I'll just be very brief. So this is one example where you can relate this theory of single valid periods to number theory. So let me just say very briefly, report on some joint work with Francis Brown on higher Green's functions, or automorphic Green's functions. I'll not say anything precise. Our preprint is not out yet. But let me just say more or less what we are doing. So there's this connection between single valid periods and the theory of heights. And as we saw in, or Archimedean heights, and as we saw in Janine's talk, this is very much related to these automorphic Green's functions. And so there's this idea that once you live within this framework of single valid periods, that the Green's function, this higher Green's functions, whatever they are, they should be single valid periods themselves. Okay, and so that's more or less what we've been doing. So here's the theorem. So let me state it like this. So if J of Z and J of W. So now I have 2 points on the upper half plane. And I'm going to assume that they parameterize elliptic curves defined over a number field. Okay. Then this is the classical higher Green's function. It could be actually any subgroup of finite index of SL2 of Z here. Is a function of 2 variables. This function sort of generalizes. So this generalizes log. You see the log of absolute value of something up here. So it's some higher version of that, whatever this means. It's usually defined in a very analytic way. And the statement is that the values of these functions is a single valid period in this sense that I explained in this talk. So this is the value of higher Green's functions. Of course, our statement is way more precise than this, but this allows us to give a very different perspective on, so let me just write one phrase, a very different perspective on these conjectures. So there are all these So there's this Gross and Zagier's conjecture on the values of this. It's not a conjecture anymore. That tells you when the values of this should be, for instance, the logarithm of an algebraic number, provided this z and w are CM points. You also have to modify a little bit this function. But this point of view we have allows us to give a new perspective on the Gross and Zagier conjecture. Essentially, we can retranslate this conjecture in terms of certain problems in algebraic geometry. And what is actually even nicer is it also allows us to go beyond the Gross and Zagier conjecture. We can see more things in this formalism than what is usually done in the literature. But let me not say much more because soon we're going to have our preprint, and then you can invite me again to talk about this in Fortaleza. Thank you.